So in the last chapter, we talked about if suppose we have a uniform B field, and then what will happen to a moving charged particle, and yeah, there will be Lorentz force, there may be a torque or a force acting on a current wire, something like that. So this time we talk about how to generate magnetic field, or how to quantify how large the magnetic field, or what's the direction of the magnetic field due to some sources. 所以上一次是讲说，有一个电场，假设有一个电场对于一个电荷会有什么的作用。那现在是讲说，有一些电流，或者是有一些所谓的 dipole moment、magnetic dipole moment， 它会怎么样产生那个，它会产生多大的磁场？所以是两个角度吧。So this is the outline of this chapter. So we talk about the magnetic field due to a current. And the force between two parallel currents. Yeah. So, and then this is the main part of this chapter, the Ampere's law, and this is one of the Maxwell equations. Previously, you have learned the Gauss law, and then in this chapter we'll learn Ampere's law, and in the next chapter you'll learn the Faraday's law. So actually, we'll have 4 formulas in the Maxwell equation. 2 of them are Gauss law. One is Ampere's law, and one of them is Faraday's law. So it's a Maxwell equation. And we'll talk about the solenoid and toroid. So yes. And the current coil as a magnetic dipole. So I suppose you have seen this in chapter 23. So at that time you learn the Gauss law, although at that time we write it as epsilon 0. And this is E rather than D, but actually the same. But although this notation is not used in this textbook, I just make use of this one to let you know that this is the Maxwell equation, and in the textbook we'll learn the integral form, and actually in Chapter 32 and 33, I'll talk about the differential form, or known as the point form. How do we derive the point form from the integral form? And then after we get the differential form, we can derive the wave equation, blah, blah, blah. So here we will talk about the Ampere's law in this chapter, but before that, we talk about the magnetic field due to a current. Magnetic field due to a current. So the magnetic field dB produced at point P at distance R by a current length element ds turn out to be like this. This expression look a bit complicated. So here we have mu0 over 4 pi, mu0 over 4 pi. So mu0 is a constant called the permeability constant mu0 which is 4 pi times 10 to minus 7 Tesla meter per ampere. Actually, I don't really remember the SI unit. Usually will provide to you, but 4 pi times 10 to minus 7 is a easy number to remember, because actually here we have 4 pi can be cancelled. So mu0 is, so mu0 over 4 pi would be 10 to minus 7. So in electrostatics, we will have K. So we will have K equals to 1 over 4 pi epsilon naught. So here we have 4 pi mu0. So this is in electrostatic. This is magnetostatic. So here we have 4 pi here, 4 pi here, epsilon mu 0. So here we have I ds. So it will be a bit more complicated than the electrostatic case, because we need to consider the cross product. For magnetic field, we always need to consider the cross product, the right-hand rule. And this is the scalar form. Scalar form, if we write that in vector form, it looks like this, because I, you can consider is a, not necessarily the vector, but there's a direction. So ds is a vector. ds is a vector. The magnitude of this is the length, and the direction of ds is the tangent line at this point. So suppose this is a curvy wire, then ds would be will not point to the same direction at all. So the direction will change according to which point it is at. And r is a vector from ds to that point you consider. So here we calculate the dB at this point, due to this part. So ds point to that direction, r is from here to p. So this one is the magnitude of r, and the direction is from here to here. So we have ds cross r. ds point to that side, and r point to that side. So b will point to this side, roughly into the page. So this is ds over ds cross r. R hat is the unit vector of r. So divide by the r square. So which means if this point is far away from that, it will be inverse proportional to the square of the distance. And also, if the current is larger than the magnetic field generated by that point, will also be larger. So if we need to consider the B field generated by this whole wire to this point, we need to integrate dB over all the segments. So that is the overall magnetic field. But dB only consider this small part, because the wire doesn't necessarily to be a constant to that point. Usually not, because even the wire is straight, and actually ds cross r will not be a constant, because you can consider, even though it's a straight line, and then we consider the point at here. So suppose ds is here, ds, r would be like this. If I consider this point ds here, then r will look like this. So you can consider for different part, dB generated by this part or this part will also be different, unless there is a special case, which is a circular loop. Suppose there's a current, then all the segments contribute to that point will be uniform. But we'll talk about it later. Actually, this page. So actually, this equation is called the law of Biot-Savart. I'm not sure is the Eastern European, maybe, I'm not sure, or Biot-Savart, something like the 有点像那种斯拉夫语，我不确定是不是。Or we can call it Biot-Savart law. So for long straight wire, carrying a current I, the Biot-Savart law gives for magnitude of the magnetic field at the perpendicular distance out from the wire. So the magnitude will be B equals mu0 I over 2 pi R. So here we have a wire going into the page. You can see the cross here means the current is going into the page. And then you use the right-hand rule. So your thumb is with the same direction of the current, and then your other four fingers will follow the direction of the B field, So it is clockwise, 顺时钟。So actually, if you have a straight wire, the magnetic field line will look like many circles with the same center. And then the point closer to this wire will be stronger because you can see that R is what? This is R for this one, and this is R for this one. So if R is larger, B will be smaller. Mu0 is a constant. 2 pi are constants. 2 I depends on how large the current it is. The larger the current is, the magnetic field generated by this current will be larger. And the distance, if the distance is farther away from this wire, the magnetic field is smaller. Okay, so if it is semi-infinite straight wire, which means that it starts from, you can consider this is an infinite straight wire, go to infinity, far away. But now we only consider a semi-infinite, maybe we just consider the upper part. This is 0, and then this wire from here to infinity. But you may ask, where does this current come from? This is another question. But just imagine there's a current going from 0 to infinity. Then the magnetic field is half of it due to the symmetric. So this is the derivation of this one and this one. Actually, you can simply imagine this is the symmetric. So if you can have this one 29.4, then 29.7 will be acceptable. So here we use the Biot-Savart law, so that the total B field generated by this infinite straight wire to this point would be like this. Actually is originally from negative infinity to infinity. So we can make it 2 times this integral from 0 to infinity because it is symmetric. And then we just substitute dB like this into here. And actually mu0 I, 2 pi are constant, so that we factor them out. R squared would be related to ds, also theta will also related to ds. Because suppose we consider ds is here, so point to this side, the current is going from bottom to top. So ds is like this, and then r is from this point to that point, and this is r hat is the unit vector, which means the magnitude of this vector is 1. The magnitude of this is 1. And then the angle between ds and r is theta, because we use the cross product, so it is sine theta. You know, here we have cross product, so we need to consider sine theta. Theta is the angle between ds and r hat, or r. So using Pythagorean theorem, we can know that r is the square root of s squared plus r squared. R is the perpendicular distance from this wire to point P, and s is the vertical distance from ds to this projection point. 就是把 P 投影到那个线上面，这个是最短 ，P 跟电线最短的距离，就是那个大 R， 然后这个是这个投影点跟那个 ds 的距离是 s。So we have R like this, and then sine theta is this one, and as you know, sine theta is actually, this is pi minus theta, and I suppose you still remember this relationship. So sine pi minus theta is r over capital R over small r. So small r is this one, and then we substitute all of them into here. So it look like this. And then we substitute 0 and infinity into this expression, and then we finally find out that B look like this. So it's based on a integral, look a little bit complicated. 啊？有现场，就把结分相应的算出来。这个的话，对啊，你可以算那个，就是你按照那个向下线你就带进去嘛，但是原则上它是不可能存在的，原则上它是不可能存在的。它可以有线长，但是如果它不是封闭的话，它不可能有电流。听明白那个意思吗？就是说，如果这个点是一个起始点，那你说这个电流从这里跑到无穷远，那这里的电流从何而来？它数学上是这样，但是原则上它就是有一点 tricky 的东西。So if we consider another case, For the previous case, the wire is a straight wire, and for this part, well, yeah, maybe it can be somehow like this. Maybe it can be somehow like this. Go to infinite far away, and then go from far away to here, and then go back. So you need to calculate for this part and for the other part. Maybe you look like this. So that it will be a current loop. So for this case, we consider the magnitude of the magnetic field at the center of a circular arc of radius capital R and central angle phi in radian, carrying current I is like this. So it is a bit different from that one. So phi is this angle. And it will be mu0 I phi 4 pi out over 4 pi out. And using the Biot-Savart law, it will be easy to derive, because actually all points from this wire generate the current at point C will be uniform and at the same direction. Because you can always consider ds is the tangent line of this wire, and r will point to the center, so they are always perpendicular to each other, and sine theta will be 1, so we can ignore it. And then the distance from the wire to the center is a constant, capital R. So it's something like this. All of them are constant, and then we integrate ds from theta to phi. So which is nothing but the length of this arc, 就是那个圆弧的长度。So this is nothing but r times phi. So one of the r, so this is nothing but r times phi. So one of the r cancel, and then we have phi here. So for a special case, if it is a whole circle, which means that for a whole circle or full circle, then here phi will be 2 pi, right? For whole circle, phi equals 2 pi. So 2 pi and 4 pi will cancel, so we only have 2r under mu0 I. So careful that we don't have a pi here. For this one, we have 2 pi r at the denominator. We have this pi for a straight wire. For a circle loop, we don't have a pi here. So now we consider a sample problem. Okay, the wire carry a current I, consists of circular arc, radius R, and central angle pi over 2, and 2 strict sections whose extension intersect at the center C of the arc. What magnetic field B does the current produce at C? So we consider 3 segments, 1, 2, and 3. Of course, there is a current wire. We don't consider far away. Maybe it go to infinite far away. Go to infinite far away, and then it form a loop. So that for this part, it generate the B field at point Z will be close to 0, because if you just substitute R tends to infinity, then the B will be 0. So you can consider like that. So now we only consider this part 1, 2, and 3. And here I for segment 1, I is from the top left to bottom right, and So ds point to this direction, ds point to this direction. Maybe for this is ds, and then r will look like this. R will look like this. So ds and r are points to the same direction, which means sine theta is 0. Sine theta is 0. So that the B field generated by part 1 will be 0. And this is the same for part 2, for the segment 2. ds point to this direction. ds point to that direction. This is ds, and r onto r. There is not capital R, small r. R point to this direction, and they point to the opposite direction, which means theta is 180. Sine 180 degree is still 0. So the B field generator part 1 and part 2 are also 0. So there are only part 3 remaining. So actually, so B1 equals B2 equals to 0. And B3 would be mu 0 I phi over 4 pi r. 4 pi r. So mu 0 I and phi is 90 degree, pi over 2. Pi over 2. So we have 4 pi r here. So pi and pi cancel, and the remaining stuff is mu 0 I over 8 r, which means that total B is B1 plus B2 plus B3, which will be mu 0 I over 8 r. Okay, so we have another one. Any questions? Any questions? No questions. Yeah. So two long parallel wire carrying current I1 and I2 in opposite direction. What are the magnitude and direction of the net magnetic field at point P? So this is I1 pointing out of the page. This is I2 pointing into the page. And it asks you the magnetic field at point P generated by this I1 and I2. So assuming the following value, I1 is 15A, I2 is 32A, D is 5.3 centimeters. 5.3 centimeters. So using the right-hand rule, we know that I1 pointing out of the page. So B1 should point to this direction. B1 should point to this direction. We use the right-hand rule. So actually, from this point to this point, and then you go for 90 degrees. So B1 point to this direction. And because this is like this, so it goes to this direction. So I2 is going to the page, So go to here and turn right for 90 degrees. So B2 point to this direction. And the next step, we need to consider the magnitude of them. So B1 is nothing but mu 0 I1 over 2 pi r. Because this one is r. And B2 is mu 0 I2 over 2 pi r. This one is r. And we only know B is 5.3 centimeter, but this is a right angle triangle, so R is nothing but D over square root of 2, which is 5.3 over square root of 2, which is 3.75 centimeter. And so B would be B1 square plus B2 square quantity square root, because B1 point to this side, B2 point to that side. So they are perpendicular to each other. So we can use the Pythagorean theorem to calculate the magnitude of the total B. So it is nothing but mu 0 over 2 pi r, and then we have I1 square plus I2 square, and then take the square root, something like this, and then we can just we have mu 0 to be 4 pi times 10 to minus 7, so 2 pi can be cancelled with it, so we have 2 times 10 to minus 7 over r is 0.0375, and then I1 is 15, I2 is 32, so B would be 118 mu Tesla. And then we need to consider the angle phi. Phi will be nothing but arctangent. So this is B1, this is B1. So B1 over B2. B1 over B2. And then you substitute the number in it. So it is nothing but arctangent I1 over I2. Because B1 over B2 or mu 0 can be cancelled, 2 pi r can also be cancelled. So B1 over B2 is nothing but I1 over I2. So which is nothing but arctangent 15 over 32. So it is 70.1 degree. Okay. No, not really, not 71. So should be 25.1 degree. Very strange. 25.1 degree. So if you consider the angle from the x-axis to here, which will be 45 degree plus 25.1 degree, which will actually be 70.1 degree. So this is what we call the theta. Any questions? Okay, so next we talk about the parallel wire, the force between two parallel currents. Because in the previous chapter we know that suppose we have a magnetic field, if we have a current wire, then there will be a force acting on the wire. Suppose the wire, the current direction is not actually the same as the magnetic field direction, and there will be a force acting on the wire. So now suppose we have two parallel currents, which means that every current will generate a B field. So the B field will generate some force acting on the other current. You can see that here we have IA, and IB. They are parallel, and suppose they have the same direction of the current. And IA will generate a B field using the right-hand rule, pointing like this. So this Y will be in a magnetic field, although it's not uniform, but for this Y it is uniform for this Y. And also this Y will generate a B field pointing roughly out of the page. So there will be a force acting on this Y too. And then we'll find that for IA, the B field pointing to this side, right? This is BA. BA is the magnetic field generated by IA. And then the current is IB. This is IB. So you can imagine DL is like that. DL is like that. Or L is like that. So suppose we can consider IB is uniform. Because in the last chapter we have DF equals I times L DL cross B. But suppose for this case it is uniform for the same wire. So we simplify it to be a simple multiplication. So it is nothing but the first acting on IB due to IA is IB times L times BA. BA is the magnetic field generated by IA. So BA is mu0 IA. Yeah, you can consider BA is mu0 IA over 2 pi d. D is the distance between them because it is parallel. So the distance is uniform for every part. So BA is like this. So you substitute BA into here. So we have mu0 L IA IB 2 pi d. And L has the same direction as the current. So you can consider it is the direction of the force is L cross BA. L cross BA is the direction of this one. So L points to this side and B points to the bottom. So L cross B points to this side. So suppose there are two parallel wire and then the current going in the same direction, then this one IA will attract IB, and IB will also attract IA. So they will attract each other. Suppose two parallel wire carrying the current in the same direction, then they will attract each other. Any questions? And the magnitude of this force is, you can use this equation to calculate it. So if so find the force. Yeah. So similarly, if two currents were anti-parallel, which means that the wires are parallel to each other, but the direction of the current are opposite. Anti-current means, suppose now IB points to this side. Then this is what we call anti-parallel. Anti-parallel, which means that IA and IB point to the opposite direction. Then they will repel each other. 他们会互相排斥。同方向它会互相吸引，反方向它们会互相排斥。They repel each other. So parallel current attract each other and anti-parallel current repel each other. So this is the conclusion for this case. Any questions?